All right, so now we're going to keep the coefficients of friction the same as the previous question. The angle of the ramp will keep the same. And we'll keep the mass of the big block the same, but this time we're going to change things up. So thus far, we've been calculating acceleration for every single example. Well, I mean, we don't, that's not what all the problems are going to ask. Some problems may change it up a bit, like this one. So in this case, they want capital M to be pulled up the ramp. And they want it to be pulled up the ramp at a constant velocity. And they're asking how heavy does lowercase m have to be in order to successfully do that. So we know that uppercase M is 4 kilograms. So do you think that lowercase m, do you think our answer is going to be bigger than 4 kilograms? Smaller than 4 kilograms? Maybe we don't even need that many kilograms to get that pulled up at constant velocity. Assuming that we give it a little bit of a nudge to get it moving in the first place. So I had to add that to the question just so we don't have to deal with static friction. Okay, we give it a nudge, break the static friction, and then let the lowercase m do all the work, trying to pull this up at a constant velocity. Okay, so I'm going to go ahead and do this the formal method, which is to make two free body diagrams and write out all the forces formally. So I'll start with lowercase m. It's much simpler. It's just got two forces on it. It's got its own gravity, which I'm going to write as mg, and it's got tension, which I'll use t, and they are equal, definitely equal. I'll use the tick marks there. And I know this because the question is asking us to get this going at a constant velocity, so forces are balanced. All right, the capital M block is going to be more complicated. So I'll draw it at an angle, going to use our ramp skills. I will define a couple of reference directions here. I'm going to go, you know what? I'll have pointing up the ramp being positive x, and perpendicular to the ramp being positive y. So for uppercase M, we have gravity pointing down. Oops. And that is not in line with x or y, so I'm going to draw components on that. Okay, so gravity will be capital M times g, and I'm going to label these F, G, X, F, G, Y. It's going to have a normal force on it. And like all the other ramp questions we've done, it's going to balance out FGY. So double tick marks here. It's got tension. So my two diagrams are not to scale with each other because the tensions are it's supposed to be the same tension because it's the same rope. but that's okay. I want each free body diagram to be accurate as an individual free body diagram. I'm not going to lose sleep over making two free body diagrams at the same time to scale. And the last force is going to be friction. So now we have friction, and the friction is going to be pointing in the negative x direction because the block is sliding up the ramp in the positive direction. That's how you decide which direction friction points. It's the direction that resists the sliding, resists the actual velocity of this block. Okay, so now I'll set up some equations, starting with the lowercase m block. That one looks nice. Just tension equals mg. Simple as that. And now into my more complicated one, so capital M block. So first of all, the normal force is equal to FGY. Which equals to mg cos theta. So that's a ramp concept there, the y component of gravity, mg cos theta. So that's kind of in the y direction. And in the x direction, it's going to be a bit more complicated. So things are going to be balanced because it's a constant velocity. So what's going to balance out what? Well, it looks like the tension, which is in the positive x direction, has to equal to the sum of FGX and friction. Those two are pointing in the negative x direction. I'll rewrite some of these. So tension equals FGX, that's using our ramp skills, would be mg sine theta. And friction would be mu times the normal. So I actually have three equations here. How many unknowns do you think I'll have? Probably three. So let's see. My first unknown, I'm going to go back all the way back to the first equation. I don't know lowercase m because that's the question. Yeah, that's the question. What does lowercase m equal? I also don't know the tension. Two unknowns. Okay, now we'll look at the middle equation. So tension's there again. I do know capital M. I do know G. I do know the angle. And I do know the coefficient. We're talking about the kinetic coefficient here because it is moving at a constant velocity. But I don't know normal force. And then sliding all the way over to the left equation, I don't know normal force. But I do know capital Mg and cos theta. So you might be able to see what we should do here. It's actually set up pretty nicely. I'm impressed. A little bit of a fluke, but things are actually worked out in order from left to right. So what I can do is use my first equation to calculate the normal force. Take that value, put it into the middle equation to calculate the tension force. Take that value, put it into the third equation to calculate lowercase m. All right, so we got a plan here. Thinking of color, running out of colors here. This might look a little ugly. I'm going to use yellow here. So the normal force equals, calculate this out. So 4 times 9.8 times cosine 60. Cosine 60 is nice. That's equal to a half. So that's going to be 19.6 newtons. Take that, substitute it in my second equation right there. So tension equals 4 times 9.8 times sine of 60 plus mu k 0.20, and now my normal value 19.6. Okay, calculator time. $37.9 or 37.87, I'll say. And now take that value and put it in my final equation right there. Solve for lowercase m. Okay, so 37.87 equals m times 9.8. So divide both sides by 9.8. And wow, I get 3.9 kilograms. It's a little surprising to me. I thought for sure I would have to have something heavier than 4 kilograms. Well, I guess that friction really is not all that much. So the 60-degree ramp helps reduce some of the load of the gravity of capital M. Friction makes it a little bit harder, but apparently 3.9 kilograms is enough.